So we covered the planetary gears the last time. Um, Planetary gears, in the planetary gears, one of the gears is not fixed. It just rotates around another one. Well, none of the gears is fixed. Well, one of them is fixed, but it can rotate. But for example, this I gear called I, can rotate around the ring or the sun gear, like this one. This is the side view, as you see. And here, one of the gears makes a full rotation around another one. And how does it do it? It does it with the help of this arm. Arm is not a gear, it's just a regular link, like just a link that makes the gear rotate around the other one. Now, planetary gears are interesting. They are a little bit more difficult, but they can achieve very high reduction or increase ratios, gear ratios, just because of the fact that there is an arm. And we analyzed them. The analysis shows that, first of all, there are two inputs to these gears. That's one thing. That is, one of the inputs is the rotation of the sun gear or the ring gear. The second is the rotation of the arm. Okay, and the rotation of the planet gear is determined accordingly. So, in order to find the rotations, the angular velocities of the planet gears, we need usually two of the, the velocity of the angular velocity of the arm and the angular velocity of the sun gear. But that sun gear's angular velocity might be zero. You might just fix this one and let this thing, the other one, rotate around the sun gear, for example. That's another possibility. But even if you specify it to be zero, that is a given. That's an input. Anyway, when we analyze it, we find that we find a similar relationship to the simple gears, only that gear ratio, which is the ratio of the radiuses and also ratio of the teeth, is equal to not the angular velocities only, but the relative angular velocities of the sun, and the J is the sun gear, I is the planet gear. Their relative angular velocities, which means it is omega 1j minus omega 1k. Omega 1I minus omega 1k is equal to the gear ratio, from which we can solve for our necessary unknown. Okay. We also derived the same thing for the internal mesh, and we found exactly the same result for the internal mesh, only that there is no minus sign there because the directions are the same. And the most general result we have is this. In general, we said, maybe I should include this thing. So in general, this is the result, okay? When you have a plus sign, it is an internal planetary gear, and when it is minus, it's an external planetary gear. Then we covered, I tried to solve a few problems. I don't know what is this. A few things are missing here. Um, a few things got erased, it seems. This is the equation. And from here, we find that, for example, the angular velocity of the planet here is 781 RPM, which is very unexpected. It's a very high number, as you see, as we find here. And I gave you one more example in which, well, an arm rotates a planetary gear, but this planetary gear is a planet both to a sun gear and to a ring gear. And we want to find the output as the rotation of the ring gear. And we found that, well, we can find it analyzing each of the gears. And also, in general, if I is the input and P is the output, the gear ratio between input and output can be written just like here, -1 to the power k, k being the number of external meshes. We divide the product of driving teeth number to product of driven teeth number. Okay. If you want to do it that way. You can also do it in the longer way. It's safer. You don't have to write this equation and analyze it one by one. I personally prefer to do it one by one. For example, I also gave this example. Let's say that you have a fixed ring gear here. So there is a ring gear that is fixed, and it's a sun gear, and in between is the planet gear, which rotates between the sun and the ring gear. So there are two meshes. One is the external, the other is the internal mesh. We write the equations from there. And we find that the angular velocity, we did it the last time, we can find the angular velocity, the arm velocity is given. And from there, we find that the angular velocity of the sun gear is, for example, 120 radians per second. So this is where we had stopped the last time. Okay, let's continue from here. Let me see if I can again copy something. I cannot copy this one. I have to draw it. What is this? So another problem. There is one sun gear here, but this sun gear is fixed, and it has 90 teeth. On top of it, there is a planet here that has 20 teeth. Okay. It is connected to an arm. like this. So this arm is the input. It goes around, and this planet gear is again a planet to another gear. And that gear is another sun gear. And it rotates like this, and this is the output shaft. Okay. This is again 20 teeth. And strangely, this has 91 teeth. Okay. And this input shaft goes on like this. I guess you understand what is going on here. So the ground is 1. This is the first link. Arm is 2, let's say. The planet is 3, and the sun gear is 4. So there are 4 links here, and this one is a fixed link, as you see. So there are two external meshes. One is 1, 2, 3. The other one is 4, 4, 3, 2, if you like. So in the first mesh, you have omega 1, 1 minus omega 1, 2 minus omega 1, 3 minus omega 1, 2 equals minus T3 over T1. Okay, this is R1, 3. In the second mesh, you have omega 1, 4 minus omega 1, 2, omega 1, 3 minus omega 1, 2 is equal to minus T3 over T4, which is R 3, I suppose. Now, obviously, we want to find a relationship between omega, input is the arm, so let's say that this would be counterclockwise. This would be omega 1, 2, and this would be omega 1, 4, I suppose. We want to find a relationship between omega 1, 2 and omega 1, 4, and omega 1, 3 is not really important here. We can find it, but it is more important to find the relationship between omega 1, 4 and omega 1, 2. And as you see, in these things, in these equations, we have omega 1, 3 minus omega 1, 2 here, omega 1, 3 minus omega 1, 2 there. So you can write the following, omega 1, 1 minus omega 1, 2 divided by omega 1, 3 minus omega 1. No, not omega 1, 3, I'm sorry. Omega 1, 4 minus omega 1, 2 is equal to, well, you can write this as this one minus T3 over T1, and the negative opposite of this one, that is the reciprocal of this one, minus T4 over T3, because I'm flipping this one so that omega 1 3s and omega 1 2s cancel each other, which I can write as follows. Minus 20 over 90 times minus T4 was what, 91 over 20, right? Yes. 20 is cancelled, minus is cancelled, so you get 91 over 90. So, therefore, omega 1, 1. By the way, omega 1, 1 is 0, okay? It is fixed. So, what we get is the following. Minus omega 1, 2 divided by omega 1, 4 minus omega 1, 2 is equal to 91 over 90. Now we can solve for omega 1, 4 from here. What do we get? Minus 90 omega 1, 2 is equal to 91. Omega 1, 2 goes to the other side. So minus 91 becomes a plus 91. So omega 1, 2 equals 91 omega 1, 4. And if we are looking for omega 1, 4, this means that omega 1, 4 is 1 over 91 omega. Okay. This is the result. And as you see, it's very interesting because you achieve a speed reduction of 91 times, which is quite unusual. With a regular gearbox, this is very difficult to achieve in this amount of space, okay? So you can say that the speed is reduced. Such gears, as I said, are used in mechanical clocks. They were used in mechanical clocks. Well, not that much anymore because, well, they are not that much produced nowadays, but such devices were used in the past to achieve very high speed reductions, as you see, but still they are interesting. Actually, Eres Hoca has another example in which, let me see, something sort of similar. Okay. Make a copy of this and try to paste it for you. This is from his transparencies. It is the 19th page, as you see. And this is very similar to what we have, only more complicated. This is very similar to this previous example I showed you. It is more complicated. As you see, if you look at the first part only, this can be divided into two parts, actually, as you see. The first part is sort of the same as the example I have given you. Okay? That is this part. Planet arm. The arm is a common arm to both of these. They have 91 and 92. In our case, it was 90 and 91. I think it is more or less the same thing. Let me see. Here you have one thing. Secondly, the output of the first part, it becomes an arm to the second part. So this is the second part. Which is identical, as you see, to the other one. 90, 91, 92. In our case, what was it? 91, 92, 90, 91. Okay. So here we have 20 teeth. Here it has 91 and 92. That's a little bit different. Anyway, in the first planet here, which is this one, as you see, N14 minus N12, which is what? Minus N12 minus, yes, N11 minus N12. If you analyze this, this is what you are going to get. Okay. Here it is even more drastic. The speed reduction in the first part is 1 over 82, 81 times the input. And in the second part, the speed reduction, it's exactly the same. It's again 1 over 82 times 81. And therefore, the total reduction is, well, 1 over 82, 81 squared of the first one. So it's amazingly, I don't know, 68 million something times reduced. The speed is reduced. For example, if the input is 2000 RPM, the output would be this much. This gearbox is almost, well, the first one rotates very fast and the second one doesn't rotate at all. The output doesn't rotate at all. Well, we can analyze this first part. Let me see. You see, these are the driving teeth. These are the But as I said, since you are not familiar with this, I would advise you not to use this driving driven thing and instead write the analysis one by one. Okay, that would be much easier for you if you do it yourself that way. For example, let me for example, you can for this thing again, okay, arm is 2, this is 1, this is 4. And then omega from which you can write omega 1 divided by this line would be 92 actually. So it is better to analyze it this way. This is the first part, for example. And the same thing can be done for the second one, which it is the same thing, so I'm not going through it again. So do you have any questions about this? Anything? Is it because it's very clear? I don't think it's very clear. In the beginning, this looks very counterintuitive actually. You have to do some problems in order to understand this clearly. You get to get used to it. Okay. Again, one more example. Okay, this is a gearbox for the famous car, as you remember, the Model T. Model T was a car designed by Henry Ford, and it is the one of the first cars that were manufactured in millions for the common people. This was about 100 years ago. But its gearbox, as you see, was some kind of a planetary gear. In this case, the input, as you see, is the arm. Which is this one, omega in, okay? And this thing is the output link, and this one is fixed. So this is fixed right here. So the sun gear is fixed. The number of teeth are given, 21, 33, 27, 27, etc. So output is S2, the second sun gear. So omega out is omega S2 actually. So you have omega out over omega in divided by omega S1 minus omega in. Okay. That would be the number of teeth, 33 times 7. So this is 7 over 11. Well, how did we get this? Again, we can analyze it one by one. We can say that this is the product of driven divided by product of driving divided by product of driven. But let's do it step by step. Let's go on it. And then for the second planetary gear, you can write this is omega S2. Actually, this is 1. Now, this is, as you see, omega out. We multiply, there is a minus sign here. We multiply them. So you get the above equation. Because this one, omega S1 is the omega P1 and omega P2. This omega P2 is equal to omega P1. So they cancel. So you get omega out minus omega in divided by omega S1 is 7 over 11, which means that omega S1, by the way, is 0, from which what we get omega out minus omega in is equal to so this is the result you have a speed reduction of well, almost 3 times. It is 36% of the input speed, as you see the output speed. Okay. This is the low gear. That is, the speed is reduced almost 3 times here, as you see. There is another thing here. Let me try to get that. Reverse gear for the Model T. Well, it looks like very similar, doesn't it? It is kind of the same thing. Here again, input is here. The output is this shaft. So this is omega in, this is omega out. And as you see, these are the gears. And this S1 is fixed. Okay. That's, well, the equations are the same actually, isn't it? We don't even have to write it. You have now omega out minus omega in is equal omega S1 minus omega in is equal to what would that be? Times 27 divided by 24 times 27. Okay. Because 27 is the same here. The only difference between this one and this one, as you see, the fixed gear has 30 teeth here, whereas here it has 21, and this one has 33, and here is 24. 30 over 24 is what? 5 over 4. Now this is 0. So omega out minus omega in is equal to minus 5 over 4. Now, since this is a number greater than 1, well, once 1 goes there, omega out is going to be 1 minus 5 over 4 will be, well, 1 minus 4 omega in, which will be minus 1 over 4 omega in. So minus 0.25 omega in. And this means this, rather this minus signs means reverse direction. as you see. Okay. Okay. Is this all clear? Or is it so hard that you cannot ask questions? I don't know what is the real issue. If you don't have any questions, I will take a break. So this example is again from Eres Hoca's notes. This is a example, let's say. So we have kind of complicated gearbox. Okay. Some teeth are not well shown here, so I'm drawing. This is kind of hard to understand. What is going on here? Okay, N12, this is the input. And whatever, N17 is the output. So this thing is 100 RPM, this thing is the output, this is rotating, but it's quite complicated, as you see. There are different gears. One thing you should notice here immediately is that the meshing between 2 and 3 and this 2 and 3 and 2 and 4, they are not planetary at all, okay? These are simple gears. That is the relationship between, for example, the angular velocity of the third shaft can be immediately found because its meshing is not planetary. So is the meshing between the second and the fourth one. The rest are planetary. For example, the fourth one, this third arm, third gear, third link acts as a arm to, for example, this thing between 4, 5, and the arm is 3, for example. And also here you have 7, 5, and 6 is like an idler gear here, but there is another planetary gear there. Again, 3 is the arm. Anyway, we can write the following. N14 over N12, for example, is equal to minus T2 over T4, which is what? But let's erase this. Let's do it from. Let me write it for 2 and 3 first. Okay. T2. T2 here is minus 40 over 20. Okay. And 1, 3. 1, 2. And n1, 4 over n1, 2 is equal to minus T4 over T, T4, where is 4? Oh, T4 over. Now it is T2, but not this, not T4, I'm sorry. It is T2 prime divided by T4. And T2 prime is this one, 36. Minus 36 over 4, 1, 24. Okay. So we can find that n13 is minus 2 n12, and n14 from the above equation is minus 3 over 2 n1. Okay, this is kind of all right. It's easier to understand. Now we have to consider um, 4, 5, and 3. 3 is the arm, as you see. So 4 is the 3 is the arm, 4 is the sun, and 5 is the planet. So you can write, or you can say, n 1, 4 minus n 1, 3 minus, so divided by n1, 5 minus n1, 3 is equal to minus T5 over T4 prime. T4 prime being this, which is T5 was what? 90 minus 90 over 30. It's minus 3. From which we can find n15, okay? It's not that difficult. You can, n14 is known in terms of n12. So, minus minus is a plus 2 n12 divided by minus n13 is 2 n12. 3. So N15 is found, as you see. It is the speed of the fifth year. Now, okay. 5 is known now. 3 is known, and now 7 is the thing. Consider the following part only so that you don't get confused. Let me just copy it here. Okay, so let's see what they are. This is 5, and this is 3. Okay. Now 5 is known, 3 is known, their speeds are known. Okay. Now the 6, as you see, uh, 5, 6, 3 is it's an internal here, where 5 is the ring, 3 is the what is it called, the arm, and 6 is the planet. Is that understandable? So you can write the following. Omega 1 5 minus omega 1 3, omega 1 6 minus omega 1 3. Now you have a plus thing. This will be T5 prime. No, T6 over 5 prime, which is T6 is 20. T5 prime is 30. Okay. From which we can solve omega 1 5, omega 1 5. I used n there, but it's okay. Well, maybe I can just keep on using n. So that's n15. N15 is minus 11 over 6 n12 minus n13. N13 was what? Minus 2 n12. So it is plus 2 n12 divided by n16. We don't know what it is. Minus n13. So that is 2 n12 is equal to 2 over 3. So minus 11 over 6. And this is n15. You are not correcting. This is n12 obviously. So minus 11 over 6, that is 2 n12. This makes 12 over 6. So this is minus 1 over 6 n12. Right? So okay. Finally, we have 673 external here. 7 is the what is it? 7 is the sun. 6 is the planet, and 3 is the earth. So you can write n1, let's say 7 minus n13 divided by minus 2, 6 over 7, which is minus 3, 6 is 20, and this is 7. N17 minus N13 is 2N12 plus 2N12. N16 is this one, minus 21 over 12 plus 2N12 minus 2 over 7. What is this? 24. So this would be 3 over 12, which would be 1 over 4. This 2 goes to the other side as a negative. Yes, that's correct. So N17 equals minus 29 over 14 N12 is the result. And if N12 is 100 RPMs, this means that N17 is minus 207.14 RPMs, which is the result. Okay. Is there a question, anything you want to ask? Ereso just solves this problem by using the, driven, driving, etc. But it is more confusing. So I did it slowly, step by step, to make it more understandable. Hopefully this is clearer if you do it this way. Okay, any questions? Okay, so much for planetary gears. I will very briefly talk about bevel gears. Well, it is really not too important, really. They are used for, let's say, non-parallel shafts. So, for example, so the shifty shafts are non-parallel. You can use the bevel gears. Actually, the equations are very similar. Only thing is the directions that you use are a little bit confusing here. In which case, we use a certain notation here, in which we say that, for example, if you use a dot, this means coming out of paper, let's say, although we have a screen, let's say paper. And if you have a plus, you have paper. So here, for example, this gear is going, this T3 is, if it rotates like here, it's hard to show if it rotates like this. This goes in, and this side comes out, as you see. There is a plus here. So this side comes out. So this point comes out as well. And here, since this comes out, this goes in, for example. Okay. The speed ratios are similar, and they are related to the number of teeth. Again, omega 1 3 over omega 1 2 is R2 over R3 or T2 over T3, and the angles also have to satisfy a certain relationship. This is again the gear ratio R2 3, as you see. Nothing too complicated except that you have the shafts are non-parallel, and therefore the directions have to be usually followed manually. Okay. For example, let me give you one example here. By the way, the most common bevel gears are, of course, bevel gears that are 90 degrees to each other. This came out to be Very cool drawing. I have to draw it myself again. This is the input shaft. There is a bevel gear here. Another bevel gear there. Oh. So this is the output shaft. So input shaft is like this. So this goes into the paper, this comes out, this goes in, this comes out, therefore this goes in. This goes in means that the output is in this direction, whatever that direction is. So it is the same direction. And the theta, this is 20, 80, this is 18, this is 60. So you have, as you see, for example, R23 is the thing is, we don't use this plus minus sign convention here because, well, what does it mean to have a plus and minus? We don't have it here. And also we have, for example, our 3, 4, let's say, 3, 4 is omega 1, 4, 3 is 3, 4. I should say Q3 prime, which is 60. So, for example, you can say R24 is equal to, well, 2 and 4 input and the output is, you just multiply these, omega 1, 3 over omega 1, 2 times omega 1, 4 over 2, so these cancel. Okay, you get T2, T3 prime, T3, T4, which is so we see that, for example, and or let's say we are using omega. Omega 1, 4 is 3 over 40 times omega 2, and they are in the same direction. Okay. I don't want to go into details of bevel gears. Only difference in the bevel gears, as I said, is the directions. You have to be careful about the directions. And the most common bevel gears are the gears that are 90 degrees to each other. Okay. Okay. Well, that's all for today, actually, and that's all for the gears. The next time I'm going to start the force analysis. So I'll stop the recording now.